Welcome everybody here. If you could please take your seats and we shall begin. I'd like to welcome everyone to this side event on atmospheric monitoring of substances under multilateral environmental agreements, specifically looking at opportunities for synergistic action. Systematic observation and measurement of the Earth's atmosphere, they're fundamental to understanding its composition and the dynamics and detecting any changes and their potential impacts. In particular, the continuous monitoring of substances regulated under the Multilateral Environmental Agreements, or MEAs, is crucial to this. So this side event will underscore and look at the critical role of atmospheric monitoring in relation to substances regulated under the Montreal Protocol, the Stockholm and Minamata Conventions. We're going to be looking at the possibilities for cooperation among the existing monitoring programs and the networks of the above-mentioned treaties, identifying opportunities to build synergies across these conventions, improving access to global resources and expertise, and also looking at how we can advance a more comprehensive and efficient global monitoring framework. So without any further ado, I would like to invite the first keynote speaker to come up, which is Megumi Seki, the Executive Secretary of the Montreal Protocol Ozone Secretariat.
Thank you very much, Stephanie. Good afternoon, everyone. So atmospheric monitoring under the Vienna Convention, we have this atmospheric monitoring activities in Vienna Convention and the Montreal Protocol. So under the Vienna Convention, it has always been a top priority issue for the parties of the Vienna Convention. The focus is mainly on monitoring of the ozone molecules and ultraviolet radiation. And then in the recent years, the atmospheric monitoring of controlled substances or substances that are controlled under the Montreal Protocol has jumped to the top of the agenda of the parties of the Montreal Protocol. Now, today for the Ozone Secretariat, the focus of this event will be the atmospheric monitoring of controlled substances, and I would like to provide a little bit of a background on this issue. So in 2018, scientists found that there was an unexpected and persistent increase in global emissions of CFC-11, and that was happening from 2012 or so. The global ban on CFC-11 production actually happened already in 2010. So there shouldn't have been that kind of an increase in CFC-11 in the atmosphere. So then also further studies, scientific studies, suggested that about 60% of that increase is originating in East Asia, and most of that was actually coming from Eastern China. So as a result of these findings, of course, parties were really surprised and alarmed, and they took action, decisive action very quickly, collectively and also individually. And especially China, they took immediate action to try to find where these emissions were coming from, and they managed to control that. At the same time, they embarked on building monitoring stations to be able to catch this kind of unexpected emissions. So I think they are quite successful in doing that building of monitoring stations in China, especially in the eastern coast. And I think they're coming up with several stations, maybe about 20 to 24 even, I heard. And not all of them are operational at this stage yet. So, thanks to the quick warning by the scientists and immediate action by the parties, the ozone layer did not suffer a big damage, and the ozone layer recovery is back on track. This incident showed that the Montreal Protocol is working, and it's working well, and at the same time, it was a wake-up call. It highlighted the need to strengthen the global monitoring network and fill existing gaps in these monitoring stations around the world, so that we will be able to detect this kind of increased concentrations and emissions in the atmosphere, and action can be taken quickly to stop such emissions. Since then, the parties have been working towards filling the gaps in these monitoring stations for improved coverage around the world. And important decisions have been taken by the parties last year to enable this kind of work under the Montreal Protocol to start fully. Now, I would like to thank all the atmospheric monitoring experts and relevant organizations such as our long-term partner, WMO, that are working with us and supporting this work to enable parties to take informed decisions on this important matter. We have also been in touch with other monitoring networks, such as the GAO network of WMO, that's the Global Atmospheric Watch Network, Chemicals Monitoring Network of BRS and Minamata Convention, CTBTO, GEMSAIR, and so on, to explore possibilities to collaborate. Today we have the BRS Secretariat and the Minamata Convention Secretariat here to discuss their monitoring activities and visions. I'm looking forward to gaining a deeper understanding of their activities and see how we can synergize with the help of WMO. So thank you.
Thank you very much, Meg, for that overview there. And next up, it is also my great pleasure to invite Rolf Payet, the Executive Secretary of the Basel, Rotterdam, and Stockholm Conventions.
Excellencies, colleagues, global air monitoring is like putting a thermometer in your tongue when you're trying to find out whether you got a fever or not. It is so vital for us to measure how effective our global conventions are. But what we see is a disproportionate network. Networks are more concentrated in the global north, and we have patches of them in the global south. So we have serious work to do there. As you know, under the Stockholm Convention, we have a global monitoring plan for persistent organic pollutants, and what we call the GMP. It provides a scientific foundation for our effectiveness evaluation of the convention under Article 16 of the convention. We have a global network of passive as well as active samplers, including stations in all regions, such as the Arctic, even Antarctica, and also remote islands. So providing us a picture of how we're doing in terms of implementation of the convention. So we have 34 POPs currently in force, 3 sets of PFAS, flame retardants, and 16 pesticides. And as you can imagine, picking those from the atmosphere can be a complex exercise if you talk to an atmospheric chemist. You need high quality equipment, you need standard samples against which to refer to it, and that is why we have such a patchiness in the monitoring stations. Good news is that we've seen drops in air concentrations of PCBs, for example, since the convention came into force. Dioxins, furans, decavidis, DDT, endosulfans, all of these chemicals continue to decline, which shows that international multilateral conventions are actually working. We've also been looking at the buildup of those chemicals in human milk. This is important because it's important that we understand how these chemicals are passed on to children, for example, where it has an impact on their development. It's also important for us to understand the impact on human health, but it shows declining levels, and that is good news. Of course, we've seen increasing levels of other chemicals, such as PFAS, and that's why the Conference of the Parties a few years ago decided to implement measures for the ultimate phase-out of PFAS, which is a group of chemicals. I don't have time to go into those acronyms today, but if you want more information, I'm quite happy to provide you with those information. Now, before I end, we also have to show that there is a link to climate change as well, because a lot of the emissions from unmanaged landfills is methane, and methane is one of the biggest emitters of pressures for climate change and greenhouse gas. And their remote sensing information has been used to detect flares from landfills, especially large unmanaged landfills from around the world. And the contribution is quite significant. We'd like to thank our collaboration with the other MEAs, Montreal Protocol, Minamata Convention, and partners in the World Meteorological Organization as well. I must also give a shout out to the universities that will collaborate around the world, and also some cities that actually maintain some of these global monitoring systems. So as mentioned before, there are significant challenges, and we need to talk about those challenges. The North-South divide in terms of monitoring capacity, the lack of this specialized equipment that can be used to detect small amounts, small quantities of these chemicals in the atmosphere, and of course, tracing the deposition, degradation, or accumulation of these chemicals in the background environment, such as in the ice, such as in glaciers, such as in the soil, and then how they mobilize and enter into our food systems, our human systems, and of course, into wildlife and other components of the environment. So I'll stop here. Just wanted to highlight the importance of having global monitoring systems, because they do and continue to support the measuring of the effectiveness of our conventions. Thank you.
Thank you very much. Next up to speak, we originally had Monika Stanjevic from the Minamata Convention on Mercury, but she's unfortunately not been able to make it. So Brenda Kukuk has very kindly offered to step in and provide her remarks on her behalf. Thank you.
Thank you very much. As Stephanie has mentioned, Monika Stankiewicz, our Executive Secretary, has sent along her regrets, but wishes us a productive session today. So the Minamata Convention is one of the newer multilateral environmental agreements, which was only entered into force in 2017, so 8 years ago. So we are new to this game under the atmospheric monitoring under our convention itself, but it's clear that atmospheric science is actually what has been studied on mercury for years and actually provided the scientific evidence to actually negotiate the treaty in the first place. So the objective of our convention is to protect human health and the environment from anthropogenic emissions and releases of mercury. And Article 22 of the Convention sets out a provision to evaluate its effectiveness. And COP5, along the way, 2 years ago, agreed to a set of 36 indicators for us to assess progress against. So the framing is there. And at our COP7 in 2027, the COP will be evaluating the effectiveness of the convention for the first time. And this will be on the basis of a report that will be developed by our effectiveness evaluation group. So this report will ultimately answer the question, to what extent are existing measures under the Convention meeting the objective of protecting human health and the environment from mercury? And this question, of course, may seem small, but it's actually a really big question to unpack. The monitoring of mercury in the atmosphere is of primary importance in answering the question, and our open-ended scientific group has collected mercury monitoring data from many monitoring programs, including data from the WMO's Global Atmospheric Watch. The monitoring data largely comes from developed countries, as Rolf has referred to, and capacity building for mercury monitoring is much needed in developing country parties. So for this, we are very much welcome. There's a new GEF program on global chemicals monitoring, which started and supports monitoring of mercury monitoring in addition to POPs, and we're very excited for this to contribute to the global data set. Overall, Article 22 in Minamata is very similar to the Stockholm Convention, and although our parties have set up different modalities and approaches for us to approach the effectiveness evaluation, we still have a lot to learn from each other and from our experiences and having a similar request, but also from other sister chemical conventions like the Montreal Protocol. And very importantly, from the scientific community around the world that's been studying mercury for years. So we look forward to a fruitful discussion today, and we look forward to new opportunities for innovation, for learning and growth together as we embark on our journey to finalize our effectiveness evaluation for 2027. So thank you.
Thank you, Brenda, for stepping in at the last minute. As you will have heard from these three keynote speeches, there's a lot to be done under atmospheric monitoring, and it's a big job in order to make sure that the atmosphere is, stays in good health, and that we can also monitor that the parties to these various conventions are also adhering to their obligations. But more on atmospheric monitoring, I will now will come up with our presenters, which I'd like to take the opportunity to introduce you to now. So first up, you will have Sofia Milona. She's the Senior Environmental Affairs Officer from the Montreal Protocol Ozone Secretariat, followed by Marilyn Beau, who is the Head of Legal and Policy Unit at the Basel, Rotterdam, and Stockholm Conventions. Unfortunately, our third presenter, Isaku Toda, who is the Senior Program Management Officer from the Minamata Convention on Mercury, couldn't be here in person, but he is sharing his presentation via a pre-recorded video link, which we'll be able to share with you. And then to round it all up, we will have Paolo Lai, who's the Chief Atmospheric Environmental Research Officer at the World Meteorological Organization, who will kind of round up the whole event. Time permitting, we hope, we will have an opportunity for a short Q&A session if we don't run over time. But in the meantime, let me invite Sofia Milona up for her presentation.
Thank you, Stephanie, and good afternoon, everybody. I would like to, let me see if I can progress. Yeah, I'm waiting for my first slide. Yeah. I would like to give you an overview of the work on atmospheric monitoring of substances controlled under the Montreal Protocol, which has been undertaken under the ozone treaties. And by ozone treaties, of course, we mean the Vienna Convention for the protection of the ozone layer and its Montreal Protocol. Let me start with some background information first, which Meg, our Executive Secretary, touched upon earlier. So the substances which are controlled under the Montreal Protocol, as most of you know, are the ozone-depleting substances, most of which are also very powerful greenhouse gases, and the HFCs, hydrofluorocarbons, which are not ozone-depleting, but are actually very potent as well, greenhouse gases. And these were introduced to the Montreal Protocol through the Kigali Amendment, which was adopted in 2016. Now, what is important to note here is that all the parties under the Montreal Protocol, they report to us production and consumption data and information on all these controlled substances on an annual basis. So basically, we have all this data, especially for ODSs, which are very long data series, and then we are able to assess the compliance of the parties with their obligations under the Montreal Protocol. Now, I see that the slides are a bit distorted. They are not what I provided, but anyway, I'll try to walk you through. So here you can see that the ODSs are actually subject to phase out, the consumption and production. So here you can see the phase out dates of the ODSs. You see the groups on the left-hand side, the groups of ozone-depleting substances or individual substances. And then you can see the phase-out dates for developed countries, which we call non-Article 5 parties under the Montreal Protocol, and for developing countries, which we normally refer to as Article 5 parties. And then you can see here that the phase-out dates for developed countries, where most of them were in the 1990s, and then the phase-out dates for developing countries were several years after. But the point is here, we have only now some small consumption of and production of 8 CFCs for both in the developing and developed countries, for especially the developed countries, and you miss the footnote there. After the phase-out dates, the parties can actually use these substances for some specific uses, but these amounts are very small. Now, when it comes to the 8 CFCs, then these are subject to not a phase out, but phase down. The situation is more complicated, as you can see here. Both developed countries and developing, they have divided to 2 groups, and then each group has its own phase down schedule. But the main thing you can notice here is that all of them will reach a plateau of between 80 to 85% from the baseline around in the period 2036 to 2047. So as I mentioned before, the CFCs were phased out globally in 2010. That's why it was very surprising. It came as a shock when the scientists in 2018 informed the world about an unexpected emission of CFC-11 globally. So you can see here the green line on this graph shows the reported production to the Ozone Secretariat by the parties. And then you can see, although it goes down and it reaches approximately 0 in 2010, when you look at the annual emissions, which are estimated by observations, as they are calculated by the 2 major networks around the globe, the red and blue lines, they show that in the years between 2012 and 2018, there was a significant increase. There was no downward trend, as we expected. So then the scientists managed to actually trace this. They found out that these kind of regional emissions, which contributed about half to the, about half of these emissions was coming from Eastern Asia. And although we have a significant decrease after 2018, this incident actually was very pivotal because this highlighted the importance of regional emissions and the fact that we have to do as much as we can to improve regional monitoring in order to pick up these regional increases. So there was a big, many discussions started from 2018 when the scientific study came out. there was a series of discussions under the key events under the Montreal Protocol where a lot of decisions were taken. Basically, the parties wanted to ask the assessment panels of the Montreal Protocol to provide more information about this issue. There was a white paper which was presented by experts in atmospheric monitoring as to how we can close the gaps in regional monitoring. And then the Secretariat was asked also to provide information on the costs, how much it will cost to do that. What is important here in the red band, as you can see here, it was a pilot project which was funded by the EU, and it started and was managed by the Ozone Secretariat. It started sometime in 2022, and we actually went to Ball Island of Bangladesh and we carried out measurements, and then we learned a lot of lessons about the feasibility of this study and what we should be aware of. So by the 2024, the parties felt that they had enough information to take informed decisions. And they came to two major decisions, but before I come to this, I want to mention the two key funds which are relevant for atmospheric monitoring under the ozone treaties. One is the General Trust Fund for financing activities on research and systematic observations relevant to the Vienna Convention. We normally refer to this as GTF for brevity. And this is an extra budgetary fund which receives voluntary contributions and then implements projects on ozone, UV, and of course from this year onwards on monitoring of controlled substances. And its activities are overseen by an advisory committee. And then of course we have the Multilateral Fund. I'm sorry, half of the slide is gone. We have the Multilateral Fund for the implementation of the Montreal Protocol, which actually helps developing countries comply with their obligations under the protocol, and this work is overseen by an executive committee. So what these decisions that were taken in 2024 said that they did was that they expanded the scope of the GTF so that it includes now controlled substances, and of course they had to expand the advisory committee of this trust fund to include experts in atmospheric monitoring. And they asked the Secretariat, in consultation with the advisory committee, to organize activities for evaluating the suitability of potential sites for monitoring emissions of controlled substances and to report to the parties, as well as to report on costs, how much this will cost. They also asked the Executive Committee of the Multilateral Fund to start thinking about putting up procedures for the financing of some pilot projects under the MLF. So the next one is about how we close the gaps, which is missing from there anyway, again. Here you see the global monitoring of controlled substances, which was available at the time that the white paper was produced in 2010 by experts. You can see here the blue and purple circles are the IGAGE, a very major network, and the red and green circles are the NOAA sites. You see, as it was mentioned before, most of them are in the northern hemisphere, and the shading here represents areas where emissions can be reliably estimated by these sites. So the question is, where can we place stations in the GAPS regions, which are basically in the southern hemisphere, in order to be able to sense regional emissions? So these typically have to be situated, according to the experts, at about 1,000 to 2,000 kilometers south, downwind of emission sources, so that they will be able to catch the emissions. And the advisory committee then, by looking at all this, they suggested 10 possible locations to set up these kind of stations. You can see here there are three, well, you cannot see very well the continents, but there are basically three on the left-hand side in South America and a bit Northern America, and then 3 in Africa, and the 4 in Asia, Eastern Europe. So they use different techniques, which we call OCEs, observing system simulation experiments, to see, for example, how the wind fields are. If we have the emission sources and we know the direction of winds, then we can place a station downwind on the understanding that this will receive, in the most part of the year, winds from that region. So then if we then implement these 10 locations, if we set up stations in these 10 locations, you see that the gaps will be filled substantially, but of course, we know that there are other programs around the world who are also doing similar things, and then we can also cooperate with them to set up more stations to fill in the gaps. So let's see what are the techniques that we use. So the scientists have told us that there are 2 techniques we can use. Either we have flask samples, we fill them in with air samples at the site, then we transport them, and then we do the analysis in very good analytical facilities. The other possibility is to have high frequency in situ sampling. That means that you do both the collection of samples and the analysis at one site. But what is very important to note is that in both cases, we have to have some critical requirements about the infrastructure. So we have to have an air sampling tower, road access, electric power and internet, air-conditioned lab, and especially no influence from local sources. And then you can see some typical sites at the bottom, which are very good stations because they are not influenced by local sources. Another very important thing is that the analytical facilities should measure parts per trillion. We are talking about very small quantities. So not all laboratories can measure these very small quantities. Another thing that the experts told us is that before we set up a station, we have to follow a phased approach. That means once we establish approximately the location we want to set up the station, then we can run flask sampling for about 6 months to check the representativeness of the operability of the site and also some basic logistics. And then if we are happy with that, then we go for 2 years sampling, a little bit higher, with higher frequency, in order to confirm the suitability of the site. Then after that, we can move on to establish either higher frequency or in situ station. So in the meantime, if we see that during the process one site is not working, then we can go back and find another site. Or if we see that during the survey period, the first blue box there, if the station operates very nicely, then we can go directly to establish the dash arrow, a very high frequency station. So what we need is that we have to have what are the essential needs for this. We need scientists who are very willing and capable to be a part of this process. We need, of course, this kind of scientific analysis to give us an idea where to place the station. We need, when we measure things, we measure concentrations, but then we have to convert them to emissions. And then we normally use inverse models to do that, and then to tell us where these emissions came from. So then we need more than one model to have an idea about the uncertainties involved and everything. Infrastructure, as I said, electricity, air conditioning, etc. Logistical support, because you need to transport the samples, overcome different customs issues, other regulations, and analytical facilities which are very able to measure very small concentrations. Another point which is not there now is that we need to have data sharing. If you do all this exercise and you don't share the data so that scientists can use them and do whatever research they want to do, then everything is pointless. So we have to place all this data on some easily accessible data servers. Sorry. Then the next yes, how much will it cost? So, sorry for this mess up of the slides. It's very hard to see, but the Secretariat was asked to basically estimate the costs. If we go for a phased approach and then we use for a 5-year measurement program at a station, then the cost, if we end up setting up a high frequency in situ station, the cost can be between 1 to 2.4 million US dollars. If we go to set up a low frequency, a high frequency flask sampling, then the cost will be less. It will be about between 550,000 US dollars to 1.2. But then we have calculated that if we find available infrastructure, then the costs can be reduced substantially. In the case, if we go and set up a high frequency station and we see that some key infrastructure is available, like a tower, building, power supply, then the cost can be reduced between 22 and 58%. If we have half this infrastructure, for example, if we need renovation, then of course the savings will be less. Here I want to say that, of course, with so much cost, you may be wondering, how are you going to do this? And then I have to say that we anticipate to receive a grant from the European Union, which is substantial sometime next year. And then we will be able to set up 3 of these sites at some locations and operate them. And at the same time, the Executive Committee of the Multilateral Fund is also looking at processes to facilitate the setup of additional stations and also make sure that the long-term financing will be there. And the parties are very keen to see this working. I'm coming now to the last decision, which was taken. It was 1 month ago at the MOP. We gave all this information, and the experts gave this information to the parties, and then they decided to ask the Secretariat, in consultation with the Advisory Committee, to continue its work on evaluating these potential sites at the 10 locations that I showed before, but now we have to involve the concerned parties, like the host countries. They have to be involved in this process. And then we are supposed to, the Executive Committee also is supposed to take all this information into account when they set up guidelines for considering a funding window to support pilot projects. So we are going to be presenting reports. We're going to be reporting to the parties next year. And the last slide. So I want to mention some key facts regarding the cooperation that we have to have. We know that knowledge of the available infrastructure is key. So working with other observation programs and networks, especially with WMO GO, we have done extensive work with, and other monitoring networks for greenhouse gases and air quality can help identify potential sites, available infrastructure, because we know if we have available infrastructure like the towers, which cost a lot, then the cost will be reduced. Important to have scientists, very qualified scientists in the sampling locations, and then we know that there are other programs which work on similar issues. We came up with 10 locations, but they have also some other locations, and then we can fill better the gaps around the globe. And in the end, something which is not mentioned is the data sharing, as I said before, because we need to make sure that the data is shared among all scientists so that they can run their own individual research, and then we can ensure that we have good quality regional emission estimates. Thank you very much for your attention.
Thank you very much, Sophia, and apologies for that. It seems that the font, when it was picked up at this end, was being corrupted. So you have not been getting the full picture, which is kind of ironic because we are talking about atmospheric monitoring and how we don't have the full picture. So hopefully that gives you an indication of what all these conventions are up against. Next, I'd like to invite up Marie-Hélène Beau, who is from the Basel, Rotterdam, and Stockholm Conventions for her presentation.
Thank you very much, Stephanie. Good afternoon, everyone. It's my pleasure today to briefly present how the Stockholm Convention monitors persistent organic pollutants. And so I do have as well a presentation that I wanted to show you. But so during this presentation, we will indeed show how the data that is generated under the Stockholm Convention on POPs monitoring support global chemicals governance as well as effectiveness evaluation. And the presentation will also highlight opportunities to collaborate with monitoring under other MEAs, but also with scientific bodies like the World Meteorological Organization. I think I will need to wait for the presentation, which is very illustrative, so I think we are missing, if we don't see it, missing something. Okay, well, for the sake of time, so as you might know, the Stockholm Convention controls persistent organic pollutants. Persistent organic pollutants, or POPs, persist in the environment. They show also other characteristics. They bioaccumulate in living organisms. They can travel long distances. They cause also adverse effects on human health and the environment. Because they move across borders, global action is essential to address POPs. Here we go, the slides are coming. Thank you so much. So, this slide shows the current coverage of the chemicals under the Stockholm Convention. So initially, when the convention entered into force in 2004, so already 21 years ago, it has 12 POPs listed under it, which were known as the Dirty Dozen. Most of the Dirty Dozens were pesticides at the time, so you can see on the slide they are underlined. But through the Article 8 of the Convention and the scientific work of the POPs Review Committee, the Conference of the Parties listed an additional 25 POPs since then. So today, the Convention lists 37 chemicals or groups of chemicals. These include 15 pesticides, 18 industrial chemicals, and 7 unintentionally produced POPs groups. As mentioned by Mr. Payet during his opening remarks, some of the industrial chemicals are PFAS. So we have 4 groups of PFAS that are listed under the Stockholm Convention, including PFOS and PFOA. So they are not individual chemicals, they are groups of chemicals. For example, if we look at the group of PFAS, the 4 groups of PFAS that are listed under the Stockholm Convention, in total it amounts to 870 compounds related to PFAS. Of course, this only represents only a fraction of the thousands of PFAS substances currently in use. An additional set of unintentionally produced POPs, namely brominated dioxins and mixed brominated chlorinated dioxins. This group of UPOPs, as we call them, is currently under review by the POPs Review Committee. So it's currently being assessed whether it meets the POPs criteria as defined under the Convention. So the Convention establishes a comprehensive framework for controlling POPs, mainly through 4 articles. There is Article 3, which requires parties to prohibit or restrict the production and use of listed POPs, as well as their import and export, except for the environmentally sound management of POPs waste. Then we have Article 4, which allows for time-limited specific exemptions to enable parties to phase out and substitute POPs. Article 5 requires parties to reduce and, where feasible, eliminate unintentionally releases of POPs by promoting best available techniques and best available practices. And finally, Article 6 obliges parties to identify, manage, and dispose POP stockpiles and POPs wastes in an environmentally sound manner in line with the Basel Convention. So to evaluate the effectiveness of the Convention in protecting human health and the environment, Article 16 of the Convention establishes an effective evaluation mechanism. The evaluation of the effectiveness of the Convention is conducted every 6 years, and the next evaluation will take place in 2029. Under the same article, Article 16, the Global Monitoring Plan for POPs, also known as the GMP, was established to provide comparable long-term monitoring data. The effectiveness evaluation of the Convention draws on 3 main information sources, as shown on the screen. Information deriving from Article 15, which is information from the national reporting. Article 16, which is POPs monitoring data from the GMP. And finally, information deriving from Article 17, which is information related to compliance. As you know, the Stockholm Compliance Mechanism was established recently in 2023, but it's currently operational and in full-fledged mode, so it will be able to provide information for the next effectiveness evaluation under the Convention. So, the latest evaluation, effectiveness evaluation was conducted in 2023 on the basis of the GMP3 report, which is the report that is generated by the Global Monitoring Plan, which provides key monitoring data. The global report, which is considered for the effectiveness evaluation, is based on regional monitoring reports prepared by regional organization groups. All regional and global reports on monitoring are available on the Convention website. You also find monitoring data from all the regions through the GMP data warehouse, which is hosted by Risotox, which is a Stockholm Convention Regional Center located in Czechia. So UNEP Chemicals and Health Branch, so UNEP supports the GMP implementation as well as capacity building in regions. UNEP supported previous GMP through various GEF projects covering 2 periods of time from 2008 to 2012, and the latest project cycle was 2016 to 2023. So from the data that was generated through the 2 rounds of projects, UNEP developed a GMP dashboard that shared widely the data from those projects, as well as other information that is very important on laboratory capacities. There will be now a new GEF project on GMP, which is called the Global Chemicals Monitoring Program, also GCMP, which will cover the period from 2026 to 2030. And this new program would, it's a bit different from the previous rounds of projects. This upcoming program will integrate POPs, but as well as mercury monitoring across the 5 regions. So we can see here there is also already an effort to work collaboratively across MEAs. So the Global Chemical Monitoring Program supports both Stockholm and Minamata, which we heard today contributes to the effectiveness evaluation of both conventions. So this program is expected to enhance collaboration among MEAs, but also collaboration among scientific partners, including through shared approaches, joint capacity building, and coordinated monitoring efforts. So, air is one of the core media of the global monitoring plan. So the slide you see on the screen shows you the GMP air monitoring sites worldwide throughout the different cycles of the GMP. So it's all the sites that serve to monitor POPs in the air. Air samples are collected through passive sampling as well as active sampling. Passive sampling uses simple, low-maintenance devices that absorb chemicals from the air over large weeks or months, providing long-term average concentrations. Active sampling uses powered pumps to draw air through filters or subboard materials, allowing precise and short-term measurements. So it's two different methodologies for the air sampling. So on that slide, you can see results from the GMP3 report that was finalized in 2023. So for pesticides, for all pesticides actually, so including DDT, endosulfan, and HCCH, you can notice downward trends for those. While for PBDEs, dioxins, and furans, some sites showed stable or increasing trends. So this could be a sign that there is continued emissions from those POPs. Overall, these findings from African monitoring sites suggest progress in reducing environmental levels of several POPs under the convention. So, as noted also before, it's a good sign. There seems overall it's a downward trend regarding POPs air emissions in the air. But another medium that is used under the global monitoring plan is human tissues. And we wanted also to present that to you. So human tissue, including breast milk, is another core medium. So the Human Milk Survey, so this is through this program that is conducted in collaboration between UNEP and UFAO. This is through this Human Milk Survey that we are able to retrieve data on human milk monitoring. So this slide shows you the results from the human milk biomonitoring conducted over the period 2000 to 2019, so almost 20 years of coverage. So the slide shows us that there are decreasing levels of key POPs in many regions. So this decline is extremely important because it indicates reduced human exposure, especially for infants and mothers. The third medium that is used under the global monitoring plan is water. So this medium is used for water-soluble substances like PFAS. So trends in levels of PFAS listed under the Stockholm Convention help identify, of course, ongoing emissions and assess also the effectiveness of regulatory actions. However, PFAS monitoring sites are still very limited. And it's not yet possible to identify clear trends regarding the increase or decrease. But efforts are continued to improve the observance of those levels and trends over time. Now, I also would like to highlight collaborative efforts because I think that was the focus of today's side event. So, a few points here. So collaboration among chemical MEAs, in our view, can strengthen monitoring through close communication and the exchange of sharing of information and expertise. So the side event of today, I think, is a very good example in that regard. Joint efforts, such as using shared sampling sites, can produce shared snapshots of environmental conditions, as well as the status of hazardous chemicals. The UNEP-GEF Global Chemical Monitoring Program is a practical example where the Stockholm and the Minamata Conventions collaborate on monitoring for effectiveness evaluation, as well as build capacities in countries. Cooperation with scientific organizations, including the World Meteorological Organization, further enhances data quality and comparability. While technical differences between treaties must be acknowledged, practical alignment still brings important benefits for cooperation and strengthen global monitoring. So in conclusion, strengthening monitoring allows us to evaluate progress, also identify emerging risks, and support science-based policy under chemicals and waste conventions, whilst enhancing cooperation among MEAs and scientific partners. Thank you.
Thank you very much, Marilyn. Next presentation is by Aisaku Toda. He's the Senior Program Management Officer at the Minamata Convention on Mercury, as mentioned previously. Unfortunately, he's not able to be here, but we do have a pre-recorded version of his presentation. If I could ask the technicians to now play that, please.
My name is Aisaku Toda, the Secretariat of the Minamata Convention on Mercury. I really wanted to participate in this event, but I could not travel to Nairobi this time. Instead, I am delivering a recorded presentation on the atmospheric monitoring of mercury. Minamata Convention addresses a single metal element, mercury. It is a relatively young convention adopted in 2013 and entered into force in 2017. Mercury, especially its organic form, metal mercury, is very persistent, bioaccumulative, and toxic. The convention is named after a city in Japan where severe metal mercury poisoning happened in 1950s and 60s. The convention controls the whole life cycle of mercury. Its supply from mercury mining, trade, use in products and processes, emission, releases, waste disposal, and the management of contaminated sites. Monitoring and measurement of mercury is important for the implementation of the Convention. Article 19 of the Convention provides for the cooperation of parties in research, development, and monitoring. Mercury is emitted and released to air and water, deposited on land and water bodies, methylated to more toxic metal mercury by accumulating fish and other animal species and consumed by humans. Therefore, mercury monitoring includes air, both ambient and emission, water, biotic media such as fish and marine mammals, and humans. Article 22 says that the function of the parties, the decision-making body of the Convention, is to evaluate the effectiveness of the Convention using monitoring data. This article is very similar to the article of the Stockholm Convention. We have heard from Marilyn that 3 rounds of effectiveness evaluation have been conducted under the Stockholm Convention. Under the Minamata Convention, the first effectiveness evaluation is being conducted. COP4 in 2022 started the first effectiveness evaluation process, which will be concluded at COP7 in 2027. COP4 established the open-ended scientific group to put together a scientific report based on mercury monitoring and taking into account the estimation of mercury emissions and releases and the modeling of movement of mercury in the environment. The group consists of experts nominated by parties, 1 for each party, and supported by other experts in the roster nominated by parties and observers. There are subgroups looking at different environmental media, human biomonitoring, emissions and integrated analysis. For this presentation, I'm focusing on air monitoring. Much of the slides today are taken from the OESG co-chair and the air group lead, Dr. Synergistic of Environment Canada. The OESG has collected mercury monitoring data from parties and literature and looking into a number of data analysis questions. Firstly, the group is looking into the current levels of mercury in the environment, as well as emissions. The current level of mercury in the global atmosphere is somewhere between 1 and 2 nanogram per cubic meters. This level is quite low compared with conventional air pollutants such as sulfur dioxide and nitrogen oxides. This is not the level at which direct respiratory exposure becomes a problem. As I explained earlier, the problem of global mercury pollution is, with the exception of poisoning from mercury vapor in hotspots such as the gold processing sites, mainly through the bioaccumulation in fish and other food items. The second and third questions are about temporal and spatial trend, whether we can say anything about increasing or decreasing trend of mercury levels or any geographical patterns. OESG is further looking into higher level questions. The fourth one is whether the observed trend in the environmental level of mercury is attributable to changes in emissions and releases, and further to the measures taken under the UNEP Convention. It seems that the currently available monitoring data are not sufficient even to conclude on the global temporal trend, so this question is largely for the future. The fifth question is about exposure and adverse impacts. The last one is about the understanding of the processes used using environmental transport and exposure models. These questions are also largely for the future. Now I'm going into the atmospheric monitoring. Mercury is measured in different ways. Mercury is detecting using different techniques, but for air monitoring, atomic absorption spectrometry is usually used. Since the mercury levels in the ambient air is not high enough, mercury is usually trapped on cold or other surfaces through active sampling and analyzed. The mercury analysis is done manually or automatically. There are continuous monitoring instruments out there that can measure mercury levels every 5 minutes or so. However, as I will explain later, most of the mercury monitoring data using active sampling are from developed countries. European Monitoring and Evaluation Program, Arctic Monitoring and Assessment Program, monitoring programs in the US, Canada, China, Japan, and so on. There are passive monitoring techniques that are less expensive. Also, wet detection is measured by collecting precipitation. This map shows the monitoring points collected by the OESG. As you see, most of the active monitoring sites and wet deposition monitoring sites are located in the northern hemisphere. Active sampling data from southern hemisphere is very useful, including those from the Global Atmospheric Watch site in Cape Point, South Africa. Continuous monitoring and sampling from tower is conducted at that point. Also, as Marilyn mentioned, the Global Environmental Facility, GEF, started the Global Chemical Monitoring Program this year. This program is an evolution from the Global POPs Monitoring Program, where passive monitoring of mercury was added, using common monitoring sites. The data from this program cannot be used for the current first effectiveness evaluation, but we look forward to using the monitoring data for the next effectiveness evaluation cycle. The OESG is currently finalizing the data analysis report. We hope to post the draft report on the website early next year. This slide shows part of the data from the different geographical locations. The OESG is also looking into the estimation of mercury emissions releases. EDGAR database is an atmospheric emission estimation by the European Union's Joint Research Centre, also covering greenhouse gases and other air pollutants. Mercury is emitted to air from various sources. The largest source of mercury emission is artisanal small-scale gold mining. Mercury is used for about small-scale gold miners to amalgamate to extract gold. This practice not only pollutes the global environment, but also causes direct health effects to the miners and pollutes the rivers and soils. The second largest source is coal combustion, since mercury is contained in coal and other fossil fuels. Mercury is also emitted from metal smelting and cement production. The estimation of mercury emission from ASGM is a big challenge. EDGAR estimates mercury emission from energy consumption and industrial data using emission factors estimated from technological assumptions. However, ASGM sector is usually an informal sector, and the data on gold production for the mercury use are in most cases missing. Under the convention, parties are to establish national action plans to reduce or eliminate the use of mercury in ASGM. And these plans are to include the baseline estimates of mercury use. However, due to the uncertainty of the information of ASGM, it is very difficult to compare the estimation by different parties. The OESC is working to connect the monitoring data and the emission estimation using mechanistic models. The multi-compartment mercury modeling and analysis project is a joint project under the Minamata Convention and the UNEP Air Convention's Hemispheric Transport Task Force, led by Ashudasto of Environment Canada. In this program, as input, EDGAR emission inventory was used, and the Chinese official emission estimation was also used to compare the result. Natural emissions and re-emission of mercury deposited on land and water are also important for the modeling. The estimation using the mechanistic models is compared with the mercury observation data, elemental mercury, mercury oxide, and wet deposition. This final slide was presented at the side event at the Minamata Convention COP6 held last month. Models seem to capture spatial variation of mercury observation, but many regions lack observation coverage. This is where the science stands in terms of global monitoring and modeling of mercury. As Minamata Convention is a relatively young convention, we would like to learn from the experiences of other conventions. Mercury monitoring is simpler than other complicated organic substances. It has been measured for a long time as part of pollution monitoring. However, conventional pollution monitoring focuses on detecting mercury levels that are harmful to human health, and we need to monitor lower levels of mercury concentration for the global purposes. Cooperation between different conventions is emerging, including the GEF, Global Chemicals Monitoring Program, and mercury monitoring at the GAW site. We look forward to further collaboration. Thank you very much.
Thank you for that presentation, Aisaku, and I'd like to now call on Paulo Lai, who unfortunately comes last, and you're going to have to be very quick. He's the head of atmospheric environmental research under the Global Atmospheric Watch at the World Meteorological Organization.
Thank you. So I will be fast. I was asked to integrate a bit the three presentations and explain why we have no choice but to collocate what we do and our monitoring system. So if I can have the first slide of my presentation. So I'm Paulo Lai from the WMO and running the Global Atmospheric Watch program. We are global, so stations a bit everywhere, but I will share that the fact that we have, no, that's not me. The fact that we need information from many places in the world, and we are facing the fact that many regions in the south do not have enough observations. So I don't know if I can have my first slide, and I wanted to take you with this first slide to Bolivia. This is the station that we have, Chacaltaya Station in Bolivia, 5,000 to 300 meters in the Andes, 30 kilometers away from La Paz. very far from any pollution sources. And this is the inside of the station. And you see that you have inside the station plenty of instruments. This is one of our, we have more or less 400 stations running a bit everywhere in the world. And this is one of our 35 flagship stations. You have about 55 variables measured there, including ozone, including some aerosol, greenhouse gases, and mercury. And I would like to take this an example of what we do with the mercury and the fact, and if you can go to the next slide, the fact that, oh yeah, I have that. If you take the variability of the different the variables that we are measuring there, and you have an example there on the left of the general variability of mercury, total mercury, and CO and black carbon. And from correlation of all these variables, because some of them are indicators of biomass burning, some others are indicators of mining, some others are indicators of long-range transport from different regions, from the ocean. Some of them are indicators of what we get when air from La Paz is lifted up to the station. Taking all this information together using models, then you can say something that if you would have only mercury measured at the station, you couldn't tell. And I have a little sketch of the mercury cycle there. What can we say? We can say that, for example, when you have the biomass burning, then you have emission of mercury. When you have the mining, obviously, is also mercury emitters. But when you have volcanic eruptions, you also have more mercury. When you have the deposition and the rain over the Amazon, then you see the mercury going down. So this is all mercury cycle that you cannot tell if you had only mercury in your station. So this is what we have. Its collocation is not new. And when you go to the guidance documents from the Montreal Protocol, from the POP Convention, from the Minamata Convention, it is there. The recommendation is clear. You have to collocate. And on the graph, what you see is the first up, the graph on the upper side is some mercury sites from what we just heard in the Minamata Convention. On the other side, the other figure is the POP Convention, and highlighted in white or red are the stations that are actually collocated with the Global Atmospheric Watch and what we do for ozone. So you see that we have a bit of a match, but we still have lots of mismatch in the system. And to illustrate, this is easy to see on the map, but to illustrate one of the issues that we have to face, I took a very simple and silly example, and you take the code, the station codes in the three associated with the three conventions, and you see that, and you compare that to our WIGOS, so our information system codes that we have for all meteorological stations in the world, for the World Meteorological Organization, and then you see that a station that is called something, a code with a code in the one convention is called with another name in the WMO system or in another convention. And can you imagine, from a user perspective, the difficulty to reconcile all that? You also have stations that have the same code, but they are not the same place at all. So what is collocation is already an issue. And this is a very simple example, but we have also some more problematic examples of collocation. Collocation is not only about a physical place where you do the measurements together, it's also after you measured where you send the information. And each of the conventions so far have their own information system. So when you do an assessment, you rely only on the information that you get from your own information system. And this is not the best way to proceed. For the reason that I explained before, if you want to have the full picture. So we have to go from a system that is going parallel like that to a system that is a bit more integrated, yes, which is an information system that would be like that. And that's very easy to say on a PPT slide, but much more difficult to implement. And there are lots of discussion in this UNEP 7 on digitalization, on the way things are organized. You have the weather booth over there in the main center that is discussing that. We know it's extremely complicated. You need same standards. It's not only the codes of the station, it's also vocabulary. It's plenty of issues that are extremely difficult to put in place, to implement. But I would say that we have no choice. We have no choice but to do that. And perhaps the fact that AI is now a tool for integrating might be a game changer. So to conclude, and this is my last slide, is about the pros and cons of co-locating. I think obviously had to put some issues that where co-locating is not the perfect solution, and scientists, they are often asking for a very specific place, a blue tower from some scientists and a green tower from others. But I think, again, we have no choice because we don't have the financial capacity to have networks all over the world operated in a different manner, and we really have to integrate. We have to integrate for cost reasons, for the data quality, for the capacity building, because the same technicians, the same engineers are the same people at the stations, for reliability, but also for the data management, and this is the most important issue that I would like to raise. That. With that, I'm finished, and I thank you very much for the attention.
Thank you, Paolo, for being so very quick. Thank you very much to all of the presenters and Isaku, who's actually following this through the live stream. You've certainly helped improve our understanding of the monitoring already being undertaken by the conventions and also the WMO, where there are gaps and where there are potential opportunities for future collaboration, co-location, co-cost sharing of facilities, as well as other practical options for enhancing monitoring capacities. And with that, I think we need to close for the next side event. And thank you very much for your attention, and thank you for coming.
Using Shopify POS has really created that connected tissue from in-store and online. It's really seamless and easy.